Whether you build, design, sell, use, maintain, or consult, I think you're going to get a really good understanding of how to reduce dust at a conveyor load zone today. Now, we use some of these terminologies a little bit differently, and sometimes you'll hear us say conveyor load zones. Sometimes you'll hear us say conveyor transfer points. Basically, what we're talking about today is trying to reduce dust as one belt dumps onto another belt. So here's what we're going to cover today, gang. We're going to do a quick review of that October webinar. So if you joined us, awesome. If you weren't able to join us, we'll give you a quick recap of that. I'm going to give you the latest as what we know right now as of December 2023 on this proposed rule from MSHA on silica dust. And then we're really going to get into the good stuff. And specifically, what I want to share with you today is the techniques to slow air movement. In our previous webinars, we talked a lot about some of the performance components that help reduce dust: skirting, wear liner, belt support. All those components are what we call performance components, and they're critical at controlling dust and spillage at a load zone or a transfer point. But what I'm going to talk about today is another part of the technique to reduce dust, and that's slowing the air speeds inside of a transfer point. So we're going to really look at that in depth today, and you're going to get some good stuff here that's going to be pretty useful. So here's the scoop on the rule. This is a little bit of a review of our October webinar. This rule was announced on June 30th of 2023. It basically says that MSHA is going to reduce the PEL, permissible exposure level, in half. Okay, so basically what mines are going to have to do is they're going to have to sample their dust, take readings, and if their dust exceeds over an 8-hour time-weighted average, it exceeds the new PEL, then they're going to have to take some steps to comply. And those steps to comply are going to be complex. There's going to be monitoring for health. There's going to have to be lots of paperwork and documentation. So it's going to be kind of complex. Now, Martin Engineering's not experts on this rule. We're not attorneys. We're not industrial hygienists. Where our expertise lies is in how to control that dust, specifically at belt conveyors. So if you have a dust problem at your facility, and you can track the source of that dust from belt conveyor load zones, this is for you. Just a quick update as of Tuesday, December 12th. MSHA Secretary Williamson gave an update. Maybe I saw this in Pit and Quarry magazine, I believe, last week. Basically, he said that there will be an update published in the fall 2023 United Agenda of Regulatory Actions. That's not expected, although it's called the fall update. That's not expected until after the first of the year. More recently, there was some wording in last week's MSHA stakeholder call. So basically what MSHA does is every quarter they do a stakeholder call, and anybody that's a stakeholder in MSHA can join in, kind of hear from MSHA on what's going on in that world. And at that, their most recent quarterly update was Wednesday of last week on the 6th. And basically the comments, the quotes from that call were, there will be no secrets in regards to this. They will train their MSHA staff. There's going to be plenty of guidance on this rule, and they really want to minimize confusion around this rule and at the same time maximize protection against workers' health concerns that come along with silica dust. So it sounds like it's progressing forward. How soon you'll start to hear from inspectors, things like that, that's TBD. That's to be determined. But the language that's being used is quite gives us a lot of confidence that this is going to continue to progress forward. three engineered controls that MSHA is going to recommend or really require mines to use to comply with this new rule. And those three engineered controls are suppression, collection, and what we call containment. Today, I want to talk a little bit further about containment. So containment is an engineered control that should help you comply, will help you comply with MSHA rules or dust that you might have at your facility. Containment is it's a term that Martin Engineering coined many, many years ago. It's an inexpensive mechanical solution to controlling dust. And it's the idea of capturing dust and spillage before it escapes. And then this really important piece is to slow the air velocity to under 200 feet per minute by the time this air gets to the exit point of this chuted or containment area. So let's talk a little more about containment and really what's the story here with this idea of containment. Now it is an engineered control. There's no reason why it won't help you comply with controlling dust. And when we really look at dust, we have to take into consideration that dust is really a formula of the particle size, the cohesiveness of the material, and three, the velocity of air that it's exposed to. Let's break this down a little bit more here. If you're using dust collection system, that is really irrelevant to how much work you're doing to prevent the dust. If you're using dust collection system, fine, great, good for you. But dust collection is not doing anything to reduce the amount of dust that is created. It's letting as much dust be created as you possibly want inside of that transfer point, and then using mechanical equipment to vacuum it off. Right? So what we can do, we can increase the particle size or the cohesiveness by using some sort of dust collection. What we're going to talk about and what is highly recommended and highly effective is to reduce the air velocity. So you got to think of dust as cargo. You've got to think of dust as product that you're either going to sell or you're going to continue through the process. And that product is not problematic. The air that it's exposed to is the real problem, which creates dust. So we'll talk about how to slow that airspeed down. So here's containment. If you've not seen this before, I'll draw it out for you real quick. This is our strategy of containment. If I've got a transfer point, basically material flows through this transfer point like this. As cargo travels through, the idea of containment is that no material can escape this chuted area until it gets to point B. Okay, we'll call this point A. This will be point B. By the time the material and the air gets to point A, we've slowed it to under 200 feet per minute. And you can do that with some quite simple mechanical devices here. So techniques to slow air velocity. Number one of the most important things you can do is limit the amount of air entering this transfer point. This is really important. What goes in a transfer point must come out. The more air that you put into a transfer point, you will push out of a transfer point. The more air that you push out of that transfer point, the higher the speeds. So one of the most effective things that we can do to reduce dust is to limit what we put in to these transfer points. And these photos are great examples of applications where the end user did a quick, inexpensive modification to limit the amount of air entering that load zone. They'll use simple mechanical devices, maybe a rubber curtain, like you see on the right-hand side, as that head pulley, as the cargo enters this load zone. Point A, if we refer to our previous drawing, point A, we've blockaded off in these photos, blockaded off, restricted the amount of air going in, because then we don't have to deal with that amount of air at point B as it exits. Another great example here. I wanted to show this one to you. I'm a little concerned with this photo because the rubber curtain is trimmed so close to what the expected profile of the material is. And that can cause some disruption of that material. So you got to be a little concerned with that. You want to restrict as much of that space as possible without disrupting that cargo as it enters the head chute. So limit the amount of air entering is number one. Number two is you want to reduce what we call induced air. So here's what's going on here, gang. Induced air happens at every load zone. And as cargo leaves the head pulley, it spreads out. As that cargo spreads out, it surrounds itself with air. Every piece of material surrounds itself with a volume of air. Now we can reduce that by using our step one, but we can do another thing here by reducing the induction of that air. So what happens is as that material cargo pulls air in, it lands on a receiving belt, settles, and then it pushes that air out, and we've got to try to slow it. So what we're recommending here is reducing how much of induced air you can take. And you do that by using some sort of mechanical device represented in this red to restrict the flow of material. So now that same amount of cargo pushes through, but in a tighter profile, and that reduces the amount of air that it induces. Now, there's engineering companies, you might have heard of this before. Some engineering companies call them IFT technology, hood and spoon technology. Sometimes they can be quite complex, where you're using devices to restrict the flow of material as it comes off the head pulley and as it's loaded onto the receiving belt as well. Sometimes this technique can be quite complex and quite expensive. Sometimes it can be quite inexpensive. I've seen instances where plants have hung some chains inside of their chute work like this. So as that material comes off, it hits those chains that are dangling down, and that might restrict it enough or a little bit. Sometimes a rubber curtain on there can make a difference as well. I want to show you a picture of a job that we kind of were impressed with. And what they did here is they had cargo coming off this head pulley, just as you'd expect. And instead of letting that cargo just flow off that drum with intense speed and lots of induced air, they've installed this hood device to restrict the ability for that material to spread out, and that reduces induced air. So number one, limit the air entering. Number two, reduce induced air. Number three, limit the drop height. Now, this is more for those of you that are designing or building conveyors. If you've got existing structure, not much you can do with this. But you've got to recognize that the higher the drop of material, the more turbulence that you're going to have. So if you can reduce at the design point the height of the material drop, that'll make a huge impact on your dust. So if I look at the diagram on the left, if material's only dropping, let's say 10 foot, I'm going to have a lot less dust than, let's say, material dropping. And let's really speed up this belt. The faster the belt, right? If this belt's traveling at X and this belt's traveling at Y, the faster the speed of the belt, the more trajectory of cargo you're going to have. And as that drop height increases and that trajectory increases, you're going to have a lot more air to deal with at point B. Okay, so if you can limit the drop heights, that's going to have an impact. Again, at the design point rather than after the point. If you reduce the drop heights, not only are you going to reduce dust, but you're going to reduce how much what we call impingement damage you might have on the surface of the receiving belt. Here's a couple of examples of facilities that try to reduce that drop height by adding rock boxes. And this isn't a bad idea. You've got to make sure that that doesn't cause some additional problems of chute pluggage and things like that. But if the material's dry, as somewhat lower moisture content, as what's typical with mining operations or processing operations, what can happen in a situation like what you see on the left or the right, material can build up and create some ledges in here. And then as that material builds up, it kind of slides down here. That, as Pete said, that will also reduce the damage to the receiving belt. That will help you kind of make up for some of that significant drop height that you might have. In the picture on the right, just a little more complex of an example. They've sent the material bouncing back and forth. So they sent the material here, then here, then here, then here, then here, then here, and really, really reduced that turbulent drop that they would have had they not done that. Now, this could cause some additional problems. You can have chute wearing out quickly. You can have material building up, and you might need to deal with that. But this is an incredibly effective way to reduce that drop height. All right. Number 4, the fourth technique to slow air velocity, and that's going to be dust curtains, chute enlargement, and dust bags. I've talked about these before. This might not be anything terribly new to some of you, but I want to review it real quick. I want to talk about dust curtains, chute enlargement, and dust bags. So let's talk real quick here about dust curtains. All right, dust curtains can help you slow the airspeed down. The idea of a dust curtain is to allow the cargo to exit at that point B, but not allow the air to exit, or to at least restrict some of that air as it exits to under 200 feet per minute. So this photograph on the right shows you a pretty good example of a dust curtain. Note how it's set back from that point B. It's typical that we want to set that back about a belt width. We also, if we're using multiple curtains, which is sometimes necessary, you want to space those curtains out about a belt width apart. And it's a good idea to trim those curtains to match the profile of the material as best as possible. Now, I came across this graphic for you. I want to share at the bottom left-hand corner. Just shows you how simple it is to utilize these dust curtains. 2 pieces of angle iron, some hardware, and some rubber sandwiched in between that angle iron drops down into that chute work and really has a major impact on how much dust you're dealing with. Okay, B is chute enlargement. And that's what you see on this photograph on the right. What we push through this chamber is the amount of air that we push through is going to carry dust. If we push X amount of air through this chamber, we've got Y amount of dust. But if we push that same amount of air through a larger chamber, we're going to push it through at slower speeds. And that's going to let dust fall out of suspension. So you want to increase the height of your shooted area or settling zone is what we call it. You want to increase the height to push that air through at a slower speed. And if you can, if you increase the length of that settling or stilling zone, you can add additional curtains. And then finally, C. I need to talk about this. I haven't talked a whole lot about dust bags here for a while, but this is really, really important. I did an online class just last week for a grain handling company in the Midwest. So they're handling grain. Grain is explosive, the dust is explosive, and the dust is problematic for them as well, although it's a different type of dust than what's typically found in a mine, but as problematic. So what these grain facilities had used in the past, and they wanted me to focus on this class that I taught for their group, was these dust bags. So the idea of this dust bag is that the air is pushed through a transfer point, and what you would do is you would install, this is a curtain. Okay, there's your angle iron. As that air hits that curtain, it's pushed up into these airbags or these dust bags. Now, in the example on the right-hand side, they're using 2 bags. Awesome. That just increases the amount of air that it can capture. Now, these bags are designed so the actual dust particles cannot escape. However, these bags will relieve some of the air as that bag is inflated. So you can see in the picture on the left, the fully inflated bag and the bracket that holds it. You can't see in this photograph, but there's a curtain right here. The air comes through, hits that curtain. It's then forced up into that bag, and then that relieves that pressure. Gang, we have done these dust bags for many, many, many years, and they are incredibly effective. If you're using any type of dust collection or dust suppression system, and you haven't taken a look at these dust bags, what a tremendously effective product, especially when coupled with the other strategies that we talked about. Okay, this was a dust study, and I shared this in our October webinar. If you've seen this before, great. If you've not, this is quite revealing here. So Martin Engineering, for many, many years, have used these strategies that I've shared with you today, along with some of those performance components that are important to really make significant impacts on facilities that have had dust problems. And this is a transfer point or a load point at a plant that was running coal. Okay, it's not a coal mine. It was a coal-fired power plant. And they had big problems with dust. Called us in, hey, what can we do? We took some sampling, we took some studies of how much dust they had and kind of used that as some of the guidance. You see the before and the after. The readings before and the readings after are incredibly significant at this facility. So this facility was actually able to achieve these results and decommission their dust collection pickup points on this particular transfer point. So this is one transfer point's readings. The before is with their current, or at the time, their current dust collection system running. The after is with the transfer point rebuilt using the tactics that we've discussed and eliminating that dust collector to achieve a 90% reduction in dust. So it can make a big, big impact. This is powerful stuff, gang.